What we have here is an attempt at idle control of a L28 Nissan turbo engine. The idle control of it is typically done by a different kind of solenoid, and the reason I'm using this solenoid is because I can directly activate it electrically. The correct solenoid for the system is a vacuum operated one that requires a separate circuit to control a vacuum. That's not working out with the current control, the ECU I'm using. The ECU I'm using is different for the engine as well. The ECU I'm using is for a VG30 turbo V6 Nissan engine versus an L28 inline 6. So I'm using a different computer for a different engine, and I'm using a third variable, which is this IAC, which came off of a Ford truck, I think it was. The whole point of doing all this is to control the idle of the L28 turbo. You could just let it bleed air and have a fixed idle, and that's fine, and it works, and that's what I think most people end up doing, but I like to try different stuff. So my goal was to see if I could make the ECU from a 300ZX turbo operate a Ford IAC control, idle air control, on a Nissan L28et. That's the whole goal here, just for fun. If I can do it, it's great. If it doesn't work, fine, we'll just go back to a fixed idle air bypass and just call it a day. Obviously, the reason I want to do this is because I'd like to be able to take advantage of the ECU's ability to command the idle air control up and down depending on the load of the engine, what RPM it sees. But that may just be a fruitless effort at some point. But what I want to do is just describe, first of all, the problem is using mismatched parts trying to make something work. Now, a little background. I already hooked this up and it kind of hunts on the idle. In other words, it would kind of overshoot the idle and then come back down, overshoot the idle and come back down. You could literally hear the IAC operating. I mean, it's over there clicking away, doing its thing, but it would hunt all over the place. Now, I tried that with two different ECUs. I wanted to make sure that it wasn't just an ECU abnormality. Both ECUs performed exactly the same. This thing would hunt all over the place. It also had some other weird idiosyncrasies, like on startup, it would idle really high and jump up to like 2,000 plus RPM, and then it would settle back down to about the normal, what you expect for a cold idle, about 1,200, and then eventually it would drop down to in normal control right around 800 RPM. But again, even then, it would tend to hunt around a little bit, especially when I tried using there's an AC on command in the ECU where you supply a voltage to a pin on the ECU, and it's supposed to bump the idle up to maintain the RPM with the load of the AC compressor. That was also hunting around. So the bottom line is I'm trying to see, why does it hunt? Now, my theory is that obviously the mixed match components probably have everything to do with it, but my theory is that the idle air control, which I think is designed for a 4-liter engine out of that truck, is simply passing too much air based on the pulse width modulation that the ECU gives it. So for instance, it's like doesn't have good resolution. In other words, even the shortest period of time of on passes too much air when it overshoots, and it's got to try to compensate. So with that in mind, if that's the problem, I guess there's a couple of solutions. One is I guess I could block off these ports. I don't know if that would do any good or not. But what I've decided to do is I would take this transistor. Now, how I operate it. This is a 10 ohm coil. The ECU is not designed to drive a 10 ohm, approximately 1 amp coil. So in order to get around that limitation of the ECU not matched to the IAC, I built this transistor controller, which is a PMP TO3 style transistor. I happen to have one in stock. I know it's probably not the most ideal component for power control, but I had it. I'm going to use it. I originally had it set up to operate in a saturation mode. That is, when you would give it when you pull it to ground, which is what this ECU does, it pulls it to ground, it would turn on the transistor and it would operate the IAC at full volume, full cycle. In the saturation mode, it It wouldn't get hot without a heat sink or anything. It was fine. Well, I wanted to operate it out of the saturation region and into the active region of the transistor. By that I mean it's acting not like a switch, but more like an amplifier. So with that in mind, I'm able to dial back the amount of current flowing through that. Unlike an on-off switch, now it's more of a variable air supply. You can still turn it on and off, obviously, by controlling the signal to it, but you can cut the amplitude of the throw. Imagine a dimmer switch on a light bulb. You have the dimmer switch all the way turned up and you turn the switch on and off, or you crank the dimmer switch down to the halfway point and then crank it on and off. So my idea was if I flow less air, maybe I'll get better resolution of this IAC to match the engine requirements for idle control. So the first thing I did was I built I used the PNP. It's even a germanium. I just happen to have one. PNP transistor because it works with a negative signal. The current flows through the base to the ground. That's how it turns on. I added the heat sink to control the heat buildup in the active region where the transistor actually dissipates considerably more power through it because it's not just fully turned on. And then I added this little pot. I had a fixed resistor here. That resistor value was determined to make sure that this thing was activating in saturation and limit the current. So that way I can never like overcurrent the transistor. That'll always keep you in saturation. There's no reason to go any lower than this number here. But if I add resistance to this signal circuit, that will bring it into the active region and then I can control it. So let's do a demonstration of that. I hope you can see that on the camera here. Here's the piston, and I'll try to zoom in so you can see a little bit more. Let me zoom. All right, hope you can see it move. Now I'm gonna put it into full saturation mode. So I turn this pot back. Now this pot is essentially 0 ohms, and this is going through that resistor. And we turn on the transistor. Let me click it on. Okay, we are now as open as that can be. Right. I don't know if I'm just hoping this shows up on the camera. I'll try to get a better view here. I'll turn it off. On. Hope that's coming out. But if I go into the active region, now I'm just going to leave it turned on. I'm going to start backing that piston off. Maybe you can see through better that way. Can you see that movement? That's pretty much fully closed. A tiny little bit of air gets through. That's fully open. So you can basically control the airflow through that with the pot. So, I mean, I guess you could just use this as a fixed idle bypass if you wanted to set the idle. You know, just forget duty cycling it. Just adjust your idle speed using this pot. It's sort of like using a fixed screw to hold the throttle plate open. But so my plan is to play with this while it's duty cycling. You can hear how much gentler that is. That's probably opening about 30% of full throw. Now we'll do it back to full throw. This is full on. You'll hear the dramatic change in the So anyway, that's the plan. The heat sink is controlling the transistor. Without that heat sink, that transistor would get hot real fast in the active region. I've already tested that, and sure enough, I mean, you run that thing in the active region for a few seconds without a heat sink, it will get warm. It's rated for 35 watts. It's a vertical out. It's a SK 3034, which is a PNP TO3 germanium transistor used. It's designed for a vertical out, so it's of a transistor TV, of a television set, which is a pretty high current application. But I'm sure the 35 amps assumes it's hooked up to a heat sink. If you take that heat sink away, and that 35 amps, that 35 watts is what it's rated for, that drops real fast. You know, if you take the heat sink off. And if it dissipates all 12 volts, you know, then it's probably going to be pulling, 10 watts plus. So we want to use that heat sink to control that. But I think with the heat sink on, you could probably activate it in that active region with just a minimal opening of this coil for quite a period of time. I didn't notice it getting, even the tiniest bit warm. So again, you could use this as a way to just set the idle. If you just forget the signal, forget cycling it, don't pulse with it, just turn it on and adjust your idle accordingly. I know it's kind of overkill for cracking a throttle open, but I'm primarily doing all these kind of things because I like to experiment with stuff. This may not be the final configuration. In fact, I'm probably sure it wouldn't be. I'd probably go to a MOSFET or something like that for the control. But I have the transistor. I'm trying to see really if it's even possible to use this IAC on that engine that it was not designed for, with a computer it was not designed for, and still get acceptable results with holding the RPM constant. And again, that's just to try to get the RPM to operate the way the FSM states it should, i.e., it should operate at a particular RPM with no load, a particular RPM with the AC on, particular RPM. I think there was one other condition. I can't remember what it was. I think it has automatic or manual, but I don't plan on using automatic or manual. So, battery op. That was the other thing. I think it looks at battery voltage. If the battery voltage drops below 12 volts, it cranks up the idle. If the AC switch is turned on, it cranks up the idle. And if neither of those are a problem, in other words, the voltage is over 12 volts and the AC is off, it adds no additional pulse width to it, but it does maintain a pulse width that should keep it right around 800 RPM. Anyway, that's it for now. I just wanted to show you where we are. And I'll be installing this on the engine in a little bit and play with this pot and see what I can do as far as trying to dial in that RPM. Thanks for watching.